For the last 50 years, mainstream cognitive psychology has treated the human mind like a clean, linear computer. The dominant models of how we process mathematics look exactly like a flowchart. You take in an input, represent the number, retrieve an algorithm, and compute the result in your working memory. In this framework, individual variables, like a student's mood or motivation, are treated as irrelevant. They are written off as error variants. They are viewed as background noise to be mathematically filtered out, so researchers can focus on the raw cognitive machinery. But when we examine how students actually learn, dismissing that emotional static is a structural error. The assumption that we can separate the process of calculating from the emotional state of the calculator is empirically false. This data reveals the scale of the problem. Mathematics anxiety has a massive negative 0.82 correlation with a student's self-efficacy. We also see that same anxiety correlates severely with a drop in motivation, down 0.64, and a collapse in self-concept at negative 0.71. These numbers dictate outcomes far beyond a student's desire to enroll in calculus. They act as an immediate constraint on active thought, dictating how the brain performs in real time, right in the middle of solving a problem. Emotion is not experimental noise. It is a structural determinant of mathematical performance that dictates whether a student can use the knowledge they've already mastered. To understand the mechanics of how an emotional state degrades cognition, we look at Michael Eisensek's processing efficiency theory. We can visualize this using a working memory capacity buffer. It is a limited volume container that holds the active processing power you have available at any given second. For low-load tasks, like quickly counting a few dots on a screen or retrieving a basic fact like 3 plus 5, this buffer barely registers the effort. The problem occupies only a tiny fraction of the total volume. When the task becomes complex, like two-column subtraction where you have to borrow, say 34 minus 19, the brain requires significantly more space. You have to hold the borrowed 10 in your head, subtract 9, and keep track of the remaining 10s. That sequence fills the majority of your active buffer. Under Eisensek's spiral, math anxiety manifests as internal rumination, preoccupying negative thoughts racing through the subject's mind during the test. This rumination acts as a parasitic background process. It immediately consumes a significant portion of your memory buffer. If this happens while you're trying to borrow a 10, the buffer overflows. The regrouping operation is pushed out, and the mental calculation crashes. We have empirical proof of this buffer overflow from a dual-task study conducted by Mark Ashcraft and Elizabeth Kirk. They first equated all their participants for baseline mathematical skill to ensure ability wasn't a hidden factor. They then gave these subjects a heavy cognitive load, solve complex arithmetic problems that required carrying while simultaneously holding 6 random letters in their memory. Under that maximum cognitive load, subjects with high math anxiety suffered a 39% error rate. The low anxiety control group, operating with the exact same baseline skills, failed only 15% of the time. The anxiety group also demonstrated local avoidance. They used a rapid speed-accuracy trade-off, rushing through the session and failing the problem simply to escape the cognitive discomfort of the test. Math anxiety degrades a subject's computational architecture by creating an artificial shortage of working memory. External pressure, from social evaluation to strict deadlines, triggers the same depletion of resources. Researchers Cyan Baylock and Thomas Carr designed a study to test how students with different memory capacities handle novel problems under pressure. They used modular arithmetic, like the formula 51 is congruent to 19 modulo 4. Solving this requires a multi-step sequence. First, subtract 19 from 51 to get 32. Then divide 32 by the modulo 4 to get 8. Finally, confirm that 8 is a whole number. This sequence relies heavily on working memory. When Bylock and Carr placed students under pressure, introducing monetary incentives and the threat of peer evaluation, the results revealed a paradox about who actually failed. This graph tracks performance across pressure levels. Participants who tested with the highest baseline working memory capacity suffered the most severe performance declines. Low-capacity students remained stable, while the top-tier performers plummeted. Why would high-stakes testing disproportionately harm the performance of the most capable students? High-capacity individuals naturally deploy efficient, resource-heavy computational strategies that rely entirely on their superior working memory. When external pressure hijacks their working memory with distracting thoughts, their specialized approach is crippled. For top performers, this leads to a catastrophic drop in accuracy. In high-stakes environments, the very strategies that make high-capacity students successful become their primary cognitive vulnerability. This parasitic load effect is also triggered by stereotype threat. This occurs when an individual is exposed to a negative, self-relevant stereotype about their demographic group right before a task. The burden of disproving that stereotype consumes the same active processing power as the math itself. Bylock found that women exposed to negative gender stereotypes only showed performance degradation on novel, high-demand problems. Their accuracy on simple tasks remained the same, confirming the working memory overflow model. fMRI data from Crendel and colleagues provides the biological evidence of this cognitive hijacking right inside the brain. Under normal conditions, subjects solving math show activation in the angular gyrus, left parietal, and prefrontal cortex, the standard regions for mathematical processing. But when operating under stereotype threat, the primary activation shifts to the ventral anterior cortex, the region dedicated to emotion regulation. Social threats and anxiety force a rerouting of the brain's problem-solving activity, shifting it from computational centers to emotional survival pathways. When we scale these laboratory findings to the macro reality of a student's life, we see how they dictate a student's entire educational trajectory. This descending cycle is the avoidance constellation. When a student believes intelligence is fixed, that belief combines with anxiety to create a permanent drag on the system. The resulting working memory depletion leads to lower achievement and a long-term avoidance of STEM fields. This loop ensures the student takes fewer advanced courses and requires remedial work, stunting their mathematical capability. On the other side is the approach constellation. Students who believe intelligence is malleable use working memory efficiently, leading to high achievement and deeper engagement with mathematics. This loop provides an affective boost, allowing students to persist through the intense cognitive demands of algebra and advanced mathematics. This creates a significant problem for educational policy. Test scores cannot accurately measure previous mastery if the subject's affective filter is compromised during the exam. Even a well-designed curriculum will fail if educators ignore the emotional environment of the classroom. Any theory of human cognition or any national testing standard is scientifically incomplete unless it accounts for the inseparable bond between emotion and working memory.